Physics students, good afternoon. Mr. Fugit here. In this video, we're going to be looking at one of the problems on your homework assignment number 8. This problem is going to be a follow-up problem to something that we solved previously. You are going to need a value that we solved in the last video. So if you don't have the value for velocity, this is the problem involving the spring where our object is being loaded up and then shot off of a raised surface. So if you don't have that value for the first part, go back, solve that problem, or maybe watch the video and get that value for velocity because we're going to need that. Now this problem, which is number 21 on your last homework assignment, number 8, is essentially a kinematics problem. We don't need to use the approach of energy anywhere in this problem. We're just going to solve it as a straightforward kinematics problem. So here, this is the problem where we are loading up an object on a spring and we're shooting it out. And we're trying to find how far the object travels. So I'm going to redraw the picture so that we don't have to deal with all the mess from the last problem. So here we have an object that is being shot off of some raised surface and ends on the ground. Now some of the values that I'm provided with, I'm told that I'm launching from a height of 1.9 meters. I believe so, or is that? No, I apologize, 2.2 meters. My fault. 2.2 meters. And I want to determine how far I travel. It is what we would call our delta x value. Now we're told a few things. So we are told that we're here on the Earth, meaning our acceleration due to gravity is 9.81 meters per second squared. And I'm told that my velocity, as I'm kind of being shot off the cliff, if you will, my velocity was, well, what I saw for in the previous problem. I believe it was 8.25 meters per second. So that's it's a little bit hard for us to see. My initial velocity right in here, 8.25 meters per second. Now, as you can guess, that is our velocity in the horizontal direction. Because since we're on a flat surface, none of our initial velocity is vertical. So, what we're going to do is kind of approach this like a kinematics problem. We're going to list out our variables and see if we have enough information to find delta x. So, we'll list some things out. In the x direction, we have delta x, which we do not know. We have a velocity value, initial velocity in the x, which coming off the cliff here, if you will, we're moving at a rate of 8.25 meters per second. Now, if you remember, kind of back to earlier in the semester when we dealt with kinematics, one thing that we said was that velocity in the x direction we'll assume remains constant. And for the most part, we're going to deal with scenarios where we have no acceleration in the x direction, so v0 is equal to v1. Acceleration in the x direction is 0 meters per second squared. Now in our problem, we're not told anything about time, how long the object's in the air, so we don't have that. Okay, so we have what looks like a good amount of information about the x direction. Now for the y direction, we're told, well, we do know our height here, how high we are above the ground. And that value is 2.2 meters. Now because we're traveling downward, our delta y is actually negative 2.2 meters, and we need to make sure we pay attention to that. Our initial velocity in the y, well, because we're coming off of a flat horizontal surface, none of our velocity is initially in the y direction. Now our final velocity in the y direction, well, it's going to be something. It's probably going to be a negative value because we are going down, but we don't know that, nor are we really asked for it here. In the last part of the problem, that is something we will solve for. And then for our object in the y direction, our acceleration in the y is negative 9.81 meters per second squared. And again, we don't have time. Not literally, but just in the problem, we don't have time, right? Now, here, we want to solve for our delta x value. So I'm going to put a star by that over here. And one thing, if you remember back to what we learned in our unit on kinematics, is that in order to figure out how far the object goes, we need to know how long it is in the air. And because all of our variables right now, all they're really telling us is that in the x direction, we're always going 8.25 meters per second. And what we really need is we need some way to limit or stop those variables. Because all we know is that we're always going 8.25 meters per second. We don't know really exactly how far we're going. We just know how fast we're going in the x direction. So what we need to figure out is, when do we stop moving, okay, both horizontally and vertically? That's going to occur when we hit the ground. So what we're going to do is we're going to use what we know about the y direction to find time, and then we're going to use that time value over here in the x direction. So I'm going to pull out my kinematic equations, and I'm going to look at the y direction. And here, I'm not told anything about v1, so I'm going to look down, and it looks like at equation number 2, I'm going to use equation number 2 to find my time. Okay, so that's the first thing we need to do, solve for time. Which again, oftentimes in physics, we're asked for one thing, but we really have to solve for another in order for us to get there. So equation 2 looks like this. Delta y is equal to initial velocity in the y times time plus 1/2 acceleration in the y t squared. So we're told in the problem statement that we don't have any initial velocity in the y because we're going on a flat horizontal surface. So this value here is going to go to 0. So delta y will then become 1/2 times our acceleration in the y times t squared. Now in our problem, we have all the variables we need except for time. So I'm going to go ahead and plug those in. Our delta y was, I believe, 2.2 meters, and going downward, which is important. Negative 2.2 meters is equal to 1/2 times negative 9.81 meters per second squared times our time value squared. Okay? We're just plugging in the variables that we know. So to simplify this down a little bit, negative 2.2 meters is equal to, well, 1/2 times negative 9.81, about negative 4.905 times t squared. So you'll notice I have two negatives, so when I divide this value over to the left-hand side, those two negatives will eventually give me a positive. So we'll divide by negative 4.905, okay, because we have an equation that is equal on both sides. We'll need to do that to the left and the right. This value will cancel out on the left. So I'll take negative 2.2, I'll divide by negative 4.905, and I'll get a value. Okay? On the left-hand side, that will look like about 0.448. Don't forget, that is equal to our time value squared. So I want to take that, take a square root on both sides of my equation, and that will leave me with the value of time, t, is equal to about 0.669. That time value will be expressed in seconds. So, again, there was a decent amount of work for us to get there, and even though the problem isn't telling us specifically to find time, we're going to need that in order to find how far we go. So once we have this time value, remember, time in kinematics is the same in both directions. Okay? 0.669, yes, seconds. 0.669 seconds. Time we have in the x direction will be the same we have in the y. So now I'm going to use that time value, and I'm going to use what I know about my velocity to find how far we travel. Okay? And if we have all four variables, we can just kind of assume the easiest equation to use. And here, that's going to actually be equation number 2, because our acceleration is going to cancel out and make that equation a little bit easier to work with. So I'll write out equation 2. Looks like this. Delta x is equal to velocity in the x times time, initial velocity, excuse me, plus 1/2 times acceleration times t squared. Now in the x direction, we don't have any acceleration. So this value on the right-hand side of our equation will go to 0, which is going to simplify things down to look like this. Delta x is equal to initial velocity in the x times time. And we know our initial velocity from the previous part of this problem, and we just solved for time. So delta x, excuse me, is my initial velocity, 8.25 meters per second, times time, which was 0.669 seconds. So when I plug those values in, 0.669 times 8.25, I get a value here, delta x equal to, looks like 5.53, I do a little bit of rounding, meters. So it was a little bit of work for us to get there. I mean, this problem doesn't really require us to use the approach of energy or springs, like we have been using in this unit, but it's a good review for us to go back and take kind of what we're learning now and see how that relates to something that we learned previously with kinematics. Okay? So if I double check my answer key, 5.53, 5.53, it looks like we're good to go. So hopefully that will get you started on solving this second part, that last kind of block of questions. The last part, just as a reminder, is extra credit. And there you're asked to solve for the overall velocity. So we'll need to find velocity in the y, and then use what we know about adding vectors to find our overall final velocity. Hopefully this will get you going in the right direction for solving this problem. And good luck.